So, ladies and gentlemen, welcome to our workshop, Machine Learning in Quantitative Finance and Risk Management. It's a pleasure that you are all here attending this, and it's great that you have interest in this kind of work. And it's a pity that we have to do it online, but on the other hand, there are more people who have the possibility to attend now, and every disadvantage has an advantage, as we always say. And my name is Kees Oostley, and on behalf of Christoph Andersen and myself, we are happy from the CWI in Amsterdam to host this workshop. And without further ado, let's get started. Our first speaker is Christoph Reisinger. Christoph is a full professor in Oxford University, the UK, and also well known as the editor-in-chief of the Journal of Computational Finance. And of course, in terms of work, he's very well known for his partial differential equation work on optimal stopping, early exercise, stochastic PDEs, and recently also on neural network-based work. And today he will talk about the Deep XVA Solver, a neural network-based counterparty credit risk management framework. So, Christoph, thank you for being here, and the floor is yours.
Okay, thank you very much, Kees and Christoph, for having me. It's the flattering introduction. So I'm going to talk about some recent work with my colleagues Atena Picarelli and Alessandro Novato about the Deep XVA Solver, which is the marketing name, but mathematically what's behind it is that we're going to use the fantastic approximation ability of neural networks to solve counterparty credit risk problems on a portfolio level, where the difficulty comes especially through the high dimensionality. So given that I'm the first speaker, I will take the liberty to start a bit more holistically and just to begin with present the backdrop of this work, which is the fantastic increase of machine learning techniques and more specifically of neural networks that have been used in the financial industry and in academia, as you're all aware, and what is also the reason that we are here today. And of course, there has been an early uptake of machine learning techniques, especially in hedge funds who have been using them for decades now to perform sort of traditional tasks of forecasting, financial time series, but then also moving on to using them, for instance, for optimal trade execution. And in particular, also, I'd like to draw your attention to the last talk today by Yu-Ying Li, who with Peter Forsyth, they've been looking at using neural networks to approximate strategies for pension funds in a purely data-driven way. And in some sense, their approach of optimizing over strategies parameterized by neural networks, this work is quite similar in philosophy of also what I'm going to talk about later. More recently than the use in sort of more of the buy side of using learning techniques in the real world measure, there's also been a explosion of works on the sell side, sort of in traditional investment banking. So in spite of some early works already in the last century, there's been in the last couple of years very strong and active research in replacing different traditional tasks in risk management by the use of learning, and particularly also deep learning. And that ranges from work in calibration, where neural networks can be used, for instance, to parameterize models and speed up an online phase in evaluating complex models. And two of our speakers today have worked actively in this area, to actually learning derivative prices, for instance, as a function of input variables such as maybe moneyness, maturities, etc., or more directly learn the hedge ratios directly. And Jashi later is going to talk about that. So there's a whole wealth of methods, and it's difficult to first get an overview of what is done and even if you are then to keep on top of the fast development. Just to be explicit of what we're talking about, and every conference on neural networks has to have a picture like this, which is sort of a graph representation, a sketch of a particular architecture of neural networks. So what we have in mind is that the neural network is a parameterized function approximation which maps a certain input, in this case in 4 dimensions, to a certain output in 4 dimensions. And it does this by concatenating a number of simple operations which can be represented as layers which are connected by these arrows here. And in this case, to fix some notation, I'm talking about the input and output dimension, which in my case will be identical, and I denote this D, so here D equals to 4. There's a certain number of layers, in this case 3, which results in 2 hidden layers. And for each of the hidden layers, we have a certain number of nodes, which I denote by nu. So I have 6 nodes in each of these hidden layers here. So what goes on in this, under the bonnet here, is that in each layer, we perform a number of operations, and they are composed of an affine transformation, which is characterized by a matrix of a certain dimension, consistent with the number of nodes, and a application of a scalar function, the so-called activation function, which is universal and scalar and applied in each of these layers. So we concatenate these 2 operations, the affine transformation with different matrices and biases, and the activation function, which is externally given. And given that we just have a complex parameterized form, and I will denote by rho the union of all these parameters, which I just stick into a high dimensional vector, which contains all the elements of these matrices and of the bias vectors. Now, given all the work that has been done in this area, as I said, it is very difficult to keep on top of what's going on, and it's very fortunate that Johannes Ruf and his co-author have very recently done an incredible service to community by, in a sense, categorizing all this work. And they went through over 150 papers that have been published in the area of deep pricing and hedging in the last few decades, and analyzed them by a number of key features that go into them. So what I'm showing you here is just an excerpt of a huge table where they group these papers depending on a number of the key characteristics, including, for instance, the features that are used to learn the prices or the hedge ratios, which, as I said, could be strike, spot, etc. What they're actually predicting, so that is typically either the price or indirectly the price through the implied volatility. But then also how the fitting is performed, so what is the loss functional in a sense, what the model is benchmarked against, what are the underlyings, etc., etc. So I strongly recommend this paper, which is due to appear just this month in the Journal of Computational Finance. So by way of advertisement from a journal, so this is I think going to be a key read, and maybe also take this opportunity to encourage anybody who's doing exciting work on this topic to just send your papers our way. We're always keen to publish work in this intersection between neural networks, learning, machine learning, and computational finance. So then, what is our little contribution in this this whole zoo of possible methods? As I indicated earlier, so we're going to apply neural networks to the problem of exposure computation, and in particular also the computation of value adjustments, which is a regulatory requirement of banks to include market fractions in the valuation of contracts, and that is done by way of so-called valuation adjustments. So what makes this mathematically and computationally a very complex task is that this has to be performed typically on the level of whole portfolios, or even the whole book of a bank, which requires the simulation of risk factors, a large number of risk factors, and the valuation adjustments depend on this high-dimensional state space. So I'm able to simulate these exposures and subsequently compute valuation adjustments on derivatives exposed to these risk factors. We are going to use a sequence of backward stochastic differential equations and apply a deep solver as proposed by E. Han and Jensen recently to solve this nested system of BSDs. And don't be put off by the technicalities of BSDs. I will come back to this in a moment, and we only have to use some of the key features, and we will see that they map extremely nicely to the problem of counterparty credit risk. And more generally in the area of exposure simulation, I also refer to Christoph Andersen, our host talk, which is just after mine. So to be a bit more concrete, let me sort of highlight the model that we are going to use, which is quite abstract, that we're modeling a large number of risky assets. So think of this as a big pool of equities or interest rates, exchange rates, commodities, etc. So the whole portfolio of underlying assets that you might have, and we model them by a large system of stochastic differential equations. So there's D of them, but we're not very specific in the model that we use at this stage. That could include also, say, stochastic volatility, stochastic rates, even if they don't feed into the derivative contracts explicitly, as we don't have payoffs on them. And then what we're looking at is a universe of financial derivatives traded and exchanged between counterparties, which are derived from these underlying assets. And so for simplicity, I will look at European contracts here, but in principle, the methodology extends also to, say, path-dependent American options, etc., etc. So I have a number, say, capital M here of derivatives, so there's likely to be large. So even if you had a single underlier like the S&P 500, so you could already have a few hundred derivatives traded on that underlying. So on top of having a high dimensional state space, we will have potentially even much larger number of derivatives traded on all these underlying. So the dimensionality sort of creeps in through that as well. And to begin with, just to fix some notation, I will consider just a single interest rate. But a key feature of the model later on will be that there's not a single source of funding, but there's differentials in interest rates between borrowing, lending, secured, unsecured lending, etc., etc. So, but I'm now first introducing an idealized market without these frictions, and we will then build on the valuation adjustments, which create the realistic prices derived from these idealized prices. Now, a key insight is that we can formulate the evolution of these derivative prices by stochastic differential equations. So as we all know that in a risk-neutral framework, the discounted derivative prices are martingales, and therefore they have a representation that I showed you here in the second equation, that the derivative prices themselves satisfy an SDE where the drift is the risk-free rate, and then there's a martingale component. So from standard Black-Scholes hedging, so we expect that in our model, this process Z is a combination of the volatilities and the hedge ratios, and that's something that we want to identify later. What is also key is that the first and the second equation here, they differ in terms of the direction that we think about them, because the first process for the underlying is a forward process that starts from a known initial spot value and then moves forward in time. Whereas the derivative price is characterized by a terminal condition where we know that the value at the maturity is equal to the payoff. So in a sense, we can think of first sampling the terminal condition and then running this SD backwards in time. So that naturally gives us a decoupled system of forward-backward stochastic differential equations. And I will, well, one of the parts of the talk will then about how we can simulate this system efficiently. So and given this idealized market, that allows me to look at a portfolio of these derivatives and formulate the value of this portfolio just as the sum of the values of all of these derivatives. And I call them the clean value because they don't include the possibility for market frictions. So that's sort of the first ingredient, just the financial market and the contracts that are traded. And this would be sort of the way you teach things on the outset to a master students about the formulation of these problems. Now, in reality, of course, it's become a requirement through Basel and since the financial crisis to include in all risk management and valuations the possibility of the default of all parties involved in the trade. So here we're taking a bilateral view where we only have two counterparties, a bank, so that would be our perspective, and a risky counterparty. And both of us are exposed to default risk. So I denote the default time of the bank or ourselves as B and of the counterparty as C. And I'll model them as exponentially distributed random variables for simplicity. And both of us hold cash accounts. So for notation, that is just denoted by B or BC is the amount of cash that we hold. And on top of that, to partially secure the deals, so the trade of this portfolio of derivatives, we will exchange some collateral. And in this work, I will assume that the collateral is a given contractually agreed function of the portfolio value. So for illustration here, I will show you here a particular, on the left-hand plot here, a particular realization of the exposure that comes from this traded portfolio between us, that comes out of a particular model that I've used later on. So the exposure can be both positive or negative. And then on the right-hand side, I will show you sort of the net exposure after exchange of collateral. In this case, the collateral was set up that it caps the exposure between -5 and 5 by, well, if we exceed the exposure above that, then a certain collateral is adapted and traded continuously to mitigate some of the risks. Now, it's become custom since the financial crisis to include in any valuation the risk that pertains from certain market friction. And so three particular risks that I will look at in this talk are the ones that come from the default of the counterparty. So that's the one we're probably most worried about, from our own default, but also from the fact that depending on the risk inherent in borrowing and lending, there will be a differential in the interest rates used. So that could be an asymmetry between interest received for lending compared to the interest payable for borrowing. And there's also a differential between secured lending, which is sort of backed up by some sort of collateral, and unsecured lending. So all the interest rates, which I assumed in the standard Black-Scholes framework to be identical, they are in reality not, and that introduces further nonlinearities in the system. So in terms of credit, direct credit risk of default of one of the two counterparties, so we'll model them as some sort of with some hazard rates. So in particular, with some constant, infinitesimally constant risk of default, so that the default time is exponentially distributed with certain parameters, lambda C or lambda B for the bank or the counterparty. And for a more general view and a very nice and didactic introduction to the modeling of counterparty credit risk and valuation adjustments, I refer you, for instance, to the book by John Gregory from a few years ago. So when I talk about XVA in the future, so X is the variable that stands for either C for credit, D for debt, or F for funding. But there's a whole zoo that continues beyond this to capital requirements, or KVA, to collateral valuation adjustments, and so on. And our framework in principle can be extended beyond that, but to keep the technicality lower, I will sort of stop at funding, which is a natural point. Now, the concrete model that we are using has been established in sort of modern mathematical finance through a number of works, especially by Damiano Brigo, Pallavicini, and their co-authors, and in a parallel stream by Stéphane Crépet and his co-authors, who've gone through the very complex and convoluted accounting relationships that come from the different funding streams and exchange of cash flows between counterparties, and putting them in a risk neutral framework and formulating them as backward stochastic differential equations. And the particular notation that I'm going to use here is in a paper by my co-author Alessandro Nuato with Jessica Biagini and Oliver. And thinking here of XVA as composed of these three valuation adjustments, credit, debt, and funding, they can be expressed as the equations that I've given you here. So I don't expect you to read this in detail, but let me just point out that there's a marked difference between the first two, which I want to illustrate first, and the last one, in the sense that the CVA, for instance, if we focus on that for the moment, is an expectation of some integral of a negative part of the differential between the actual exposure of the portfolio, so the term V hat, so that would be the idealized exposure in an idealized market, and the collateral. So this is sort of what before was this capped exposure. And we're interested in the negative part because that's what worries us in terms of default of the counterparty. So I really want to emphasize here not so much the details on how this is derived, but the mathematical structure, which will become important for the computation, that assuming, for instance, constant interest rates, so all these cash terms B here, that we can just think of them as constant, that can be taken out of the expectation. There's a recovery rate, this RC here, which is basically the fraction of losses that could be recovered from the bank. Again, this is just a constant factor. So the key here is this negative part of the exposure, which is then multiplied by the default probabilities, this lambda c here, which again we assume is just a constant. But it's intuitive that the valuation adjustments should depend on this lambda in this way. So mathematically, in this sort of simplest model, we somehow have to compute expected negative exposures. So the expectation of this differential of V minus C, and if you assume now that the collateral is a function of V, then really all we have to do is compute the expectation of some nonlinear function of the exposure. So this is why terms called the discounted expected positive and negative exposures will feature prominently later on. Now, what makes the last term, the funding valuation adjustment, different is that we have some inherent recursivity, which comes from the fact that if you add a valuation adjustment for the funding cost to your contracts, then you have to fund more, and that affects the valuation adjustments again. So there's sort of something like the snake bites itself because the valuation adjustment affects the funding and so on. So therefore, you see that in this formula for the FVA, the XVA appears again, and so the XVA, the FVA. So we will see that computationally this is a more complicated problem and results in some sort of nested application of our method later on. But for the time being, I want to focus on the first two terms, which requires only to compute sort of exposures here. Now, of course, we are by no means the first to look at this, and there have been a whole wealth of different methods that have been proposed. So if we take a step back from these complex formulas, the mathematical framework is that there's some underlying assets which results in values of derivatives. And because the exposure depends on the value of the derivative, not just at time zero, which would come out of a simple Monte Carlo simulation, but exposures at all the future times, we have to keep track of the derivative prices along all these simulated scenarios. And that, for instance, rules out traditional PDE-based methods, because if you're in a high-dimensional state space, then traditional PDE methods will break because of the curse of dimensionality. And on top of these scenario generations for both the underlyings and for the derivatives, we then have to compose further valuation adjustments along these trajectories, which may involve solving further forward or backward differential equations along these paths. So to deal with this, so in particular the fact that we have to price derivatives on all the points on our trajectory, sort of straightforward philosophy is to use a nested Monte Carlo simulation, which consists in simulating outer paths to generate the scenarios. And then for each point on the path, you run an inner Monte Carlo simulation to price derivatives. Now, done naively, this is prohibitively expensive. And therefore, there have been many improvements proposed by, for instance, by people like Brody to have an optimal trade-off between the number of inner and outer paths. So there's some optimization that can be done. And there's this recent work by Stefan Cabet, Claudio Albanese, and others about using, for instance, GPUs for very efficient implementations of this methodology. Maybe more common in practice is some regression-based Monte Carlo, where we regress the value functions of derivatives along these simulated scenarios in a Longstaff-Schwartz type way. And there's an early work, for instance, by Schöffner, but I also know that, for instance, Kees and co-authors have done work on this, and in particular, they've also looked at certain hybrid schemes where you can think about sort of generating scenarios with Monte Carlo, but then you're open to using other methods for the pricing along these scenarios. So if each individual derivative is only exposed to a much smaller number of risk factors, so it may be possible to use PD methods, the cost method, or other methods for efficient pricing. And I had a go with Kees de Graaf and Drona Kandai of trying to use sort of pure PD formulations, even in high dimensions, by using forward PDs to compute probability densities, and then backward PDs for the pricing along scenarios. And we try to tame the curse of dimensionality by a decomposition of the prices in an ANOVA type way with respect to the risk factors, and use that as a dimension reduction methodology. And for exposure computations, and there's also a very recent paper by Christina Christauer and her co-author, where they look at, for instance, a PD for valuation adjustment directly in a situation where an actual PD formulation is available, but this in low dimensions. But these would be quite specific and involve heavy machinery. Now, linking this closer to our philosophy here, there's recent work by again, Stefan Cabet and Claudio Albanese and their co-authors on a BSDE formulation and using regression type Monte Carlo methods for solving these BSDs, and then also using regression to compute quantiles of the exposures. In a sort of different philosophy, but still using deep learning methods, Pierre-Henri Labaudet, he has a quite ingenious way of using duality in situations where the counterparty credit problem can be formulated as HGB equations or equivalent control problems, and using duality to compute upper and lower bounds for a deep solution of the pricing and valuation equations. Now, our work is similar in spirit to BS in that we're using the recently introduced Deep XVA Solver by E. Han and Jensen to generate the pricing equations, the trajectories for the underlying derivative prices, and sort of to cover the whole what is called the mark-to-market cube, which is the cube of, or hypercube of derivative values with respect to all the underlying asset values. But we take this a bit further to more complex valuation adjustments by systematic recursive application of these methods. So as a one-slide summary of the Deep XVA Solver, where the authors have, in numerical tests, demonstrated that they're able to solve extremely high-dimensional nonlinear PDEs by using the equivalence between the PDE and it as a value function of a BSD to solve these backward stochastic differential equations with neural networks. So the gist is really summarized here that we start written here in a more abstract way as process X and Y, but I'd like you to keep in mind that X in our situation will always be the underlying process, which I called S before, and Y it would be the either derivative prices or valuation adjustments from the previous slides. But you have, again, sort of this one-way coupling that X is a process that runs forward independently and Y is a process which runs backwards and contains this, what is called the driver of the BSD H here. And it's set up in a way that we trying to hit a terminal condition, which is a function theta of xt. So this is what is given here. So we're hitting a target terminal distribution, and then we run this backwards. And we choose a certain, what is called the control of the BSD, this term ZS, which is a stochastic process, which we adapt in a way that we steer the process from a given initial condition, called little y here, to the target terminal distribution. And the key idea is that after discretization, which I've given you at the bottom, so for simplicity, a simple Euler scheme for both X and Y, we look at this as a control problem in this Markovian setting where we parameterize this process Z as a function of, well, time and the X process. So we're looking for Markovian controls where Z is just a parameterized function. And we trying to choose it in a way that we're getting close to the target terminal distribution. So what it is, we minimize some loss function, which is just the square difference between the target, so the theta of the simulated process at the final time step n, and the solution of the second equation here. So where neural networks come in is that we're using neural networks now to parameterize this control here. And so we do this in each time step and we introduce sort of this set of hyperparameters. So this would be in the last line here. So we're looking at a parameterized function phi. So think of this as this family of feedforward neural networks that I showed you earlier on in the talk, which contains this huge vector of hyperparameters, which are basically all the values of the matrices, offset vectors, etc. So we've sort of changed the BSD into a high-dimensional optimization problem over these hyperparameters, which parameterize the control process, which we choose in a way so as to minimize this target loss function. Now the question is, well, this seems an intuitively good thing to do because we will ensure that in some strong sense we replicate the final payoff. Well, if you think of these as derivatives, so in another interpretation in a financial background is that we're choosing the hedge ratio, which is encoded in this process Z. So the hedge ratio as a function of the underlying, so as to well replicate the payoff of the underlying at the terminal time. So viewed this way, this is a very natural way of approximating this BSD. Well, the question is there anything that we can say theoretically about this? And in fact, there's a result by Han and Long, who have a quite nice error bound, which is expressed in the way that I showed you. So if we measure both the error in terms of the Y process, so that would be the solution of the second differential equation, and the control process Z, then in a certain L2 type sense, this can be bounded by a time stepping error. So the delta T term on the right hand side, which comes from basically the Euler time stepping. So given that we have a square term on the left hand side, this is just an order 1/2 term as you would expect from the strong order of the Euler scheme. And then there's a second term which measures basically how well or badly we did in matching the terminal condition. So that's exactly an L2 term of the error that we make in hitting the target distribution at the end. Now, this is something that they have a result for which sort of tries to quantify this term in terms of the expression power of the neural network, because if the family of neural networks is rich enough that we encapsulate the true optimal control, then in theory, we should be able to make this term small. But of course, there's also the fitting error, because neural networks are notoriously hard to fit. So any error in the optimization will also show up in this term here in practice. So in that sense, I would think of this as a much more appropriate a posteriori bound, because once we have found our neural network parameterization of the control, we can simulate this second term here by sampling and just estimating the square term, which is something that comes out of our loss functional anyways. And if this term is small, then we have a good upper bound for the error of the actual processes. And this is the maximum error over all the time. So this is quite a nice result. So sort of summarizing this as an algorithm, so what we do is we generate a lot of scenarios for the underlying. So here denoted by SL, L sort of being the index of the path, and we do this a capital L times, and then we simulate some empirical loss function here, and in an outer loop we optimize over the hyperparameters, and we do this with stochastic gradient, some version of stochastic gradient descent with a certain learning rate schedule. So surely this is the most expensive part to carry out the optimization on top of our simulation routine here. And then on top of that, we can use that to compute exposure profiles. So without going into details of the algorithm here, which is very straightforward, just looking at the top line, so we have to estimate the expectation of some time integral of a function of the computed exposure, and this is done by some quadrature over the Monte Carlo path. Just to give you some sort of simple examples first, and then some more complex ones. So we look at, for instance, just as a sanity check, at examples where we know what the exact answer should be. So looking at just the Black-Scholes type model, where we have some simple derivatives and then compute expected positive and negative exposures. So the first example is just a forward contract, and that's particularly neat because in this case, of course, well, we know what the final answer is, but also remember that we are approximating the delta hedge of the contracts in this case, because the option value is just linear, so the delta hedge is constant. So if we're using rectified linear units as activation functions, then even with a single layer and two activation functions, we should be able to approximate the hedge ratio exactly. So in a sense, this is literally a zero-order test because we're trying to approximate a constant by this neural network. And we see here, so what I'm showing you here now on the left is the simulation of the exposures of this trivial portfolio of one contract, which given it's a forward can be both positive and negative. And this is simulated over 64 paths in this situation. And then of all these scenarios, we're optimizing the hedge of this forward contract. And we end up with a certain hedge ratio, and based on that, we compute now the expected positive and negative exposure. And this is sort of a plot that practitioners look at a lot. So this is now on the right-hand plot, plotted over time, the expected positive and negative exposures, which should look like a square root curve, given that there's Brownian motions involved. And there's sort of the exact solution, which is given by these dashed lines. And then in red and blue are the exposures computed by our BSDE solver. And we see that visually they agree pretty much perfectly. And then I'm showing you sort of a gray shaded area, which is a confidence interval that was computed by repeated running of the solver. So it's a fairly large variance, which comes from the fact that we only use 64 paths for the fitting. And then we're using, for the actual estimation of the positive and negative exposures in the second step, we're using a higher number, in this case, just over 2,000 of scenarios. And this was with a neural network which has 2 hidden layers and 20 nodes. But as I said, so this is a complete overfit in this scenario because a much smaller number should already give a perfect fit. So this is more a sanity check and a test for the optimizer. Now, slightly more interesting, I'm showing you here an example now for a Black-Scholes European call. So here at least the fitting is non-trivial because we're approximating the delta of this option, which is a step function at maturity, and then it's some well, smooth but non-linear function, which is non-trivially approximated by these ReLU activation functions and the feedforward neural network. Sort of same architecture as before, same number of samples. Now, what you see here is that, of course, because it's a portfolio of a single derivative, single option, then the negative exposure is 0. And the positive exposure is exactly the derivative price. And if I'm looking at the discounted positive exposure, then it is a constant. It's exactly the initial value of the option. So what we see as the blue line should be precisely a constant at the time 0 value of the derivative, given that we have a martingale. And again, I'm showing you some sort of confidence intervals. Now, we can check the approximation power of the neural network in this case and the quality of our iterative solver. So in the bottom line, there's now a few numbers. So the first one is the discounted expected positive exposure at time 0 that comes out of my Deep BSDE solver, which is 10.407. And I can compare this to the exact solution, which is precisely the Black-Scholes formula for these parameters given here. And that is 10.404. So given that we have a strike and a spot price of 100 here, and we only have an error here in the third decimal place. So this is below basis point accuracy. So even with a fairly small neural network of only 2 hidden layers and 20 nodes, we can find the value of this derivative extremely well. Now, given that this is numerical and then simulated forward in time, this line is not exactly constant, and at the terminal time, the DP here is 10.4997. So there's a large error that comes from the accumulation of the noise. But still, that's very high accuracy. Now, of course, nobody will be impressed with a solution of the Black-Scholes formula. So we then tried to use neural networks to approximate higher dimensional cases. So if I replace now the single underlying by a basket, and you could look at and explore sort of the dependence of the number of assets. So I'll just show you one example where we used 100, which is clearly something beyond what you can do with standard deterministic methods. Sort of using a similar architecture, but increasing the number of nodes here linearly with the dimensions. So we still have 2 hidden layers, but over 100 nodes now. So now I don't have a closed form formula anymore, but in the last line, I'm comparing the Deep BSDE solution to one computed with a standard Monte Carlo simulation, just run from the initial time with a million paths, which gives me a confidence interval of around 397 to 398.99. The Deep BSDE solver, again, is not constant over time because of the simulation error, but it does have a higher variation than, say, the confidence interval that comes from the Monte Carlo solver. But bear in mind that for the Deep BSDE solver, we only used 64 paths for computational efficiency, whereas for the standard Monte Carlo, I used 10 to the 6 paths. So it's not surprising that there's a much higher standard deviation. And in addition to that, this was an earlier computation which is a suboptimal regime of the learning rate. So our experience is that if we use similar learning rate schedules between different dimensionalities, there's only a very weak dependent of the accuracy and of the dimensionality. And we believe that rerunning this again with a more optimized learning rate, as we have done for the standard European call, that we would achieve a similar accuracy to here. So this really shows the strength of this neural network approach, that we can get accuracy which in some extent is largely dimension dependent and certainly breaks the curse of dimensionality. So other than sort of pushing the dimension further, I now want to show you, just as a last example, an application to the funding valuation adjustments, where we're looking at computing here the FVA, which, as I said before, has this added difficulty that we have this recursive nature, that the valuation adjustment depends on funding itself, and therefore we have this recursivity. And formulating this again as a BSD, we see that this now has this recursive structure, that the driver of the BSD for the XVA depends now on both the XVA itself and the simulated value of the portfolio that comes out of the first stage that I spent most of my talk talking about. So the two key features are, so the driver F of the BSD, which is given at the bottom in its full glory, that we have these first two terms which come from the counterparty credit risk of ourselves and our counterparty, which is something that we can evaluate from the first stage of our simulation, because we've simulated the idealized portfolio values and the collateral. And then the last line here would contain the XVA. And because the XVA at maturity of our derivative portfolio is 0, so we're aiming to hit 0 with the XVA. So rather than hitting a certain payoff like before in the derivative pricing examples, we're trying to hit exactly 0. So that translates now into a new formulation of this deep BSD algorithm, where we now, well, first generate the scenarios of both the underlyings and the derivative prices along all our trajectories, using the method that I just showed you before. And then in the second step, we plug this into a second BSD with a driver, which is now just a function of our previous results. And we try to find the control of this BSD so as to steer it towards 0. So our loss function now is an empirical mean of the squares of the values at time t. So this is what we're minimizing. And again, we're minimizing over the parameterized control of the BSD. So again, parameterizing this now with a new neural network, so denoted here by zeta. And we were trying to find the XVA both at initial times, so-called gamma here, and at future times. And sort of a key advantage of formulating the problem in this way is that as a byproduct of the computation of the portfolio values and of the XVA, we also get the sensitivities basically for free, because we directly parameterize the hedge ratios of the options and the gradient function of the XVA. Also XVA hedging, for instance, is something that comes out of our algorithm automatically, because of formulating in a good way the primitive of the approximation, which is exactly the hedge ratios. In that sense, I think this is more natural than a parameterization of the value functions. And if it was second order sensitivities you're interested in, then basically you have to just differentiate your parameterized form here, which is something that, of course, in deep learning has been very well established by using automatic differentiation routines, etc., backward propagation and so on. Now, we can now also quantify the errors of this multi-stage procedure by using the previous result that I showed you from the Han and Long paper, and basically quantifying the propagation of the error of the neural network from the first stage of our algorithm using sort of standard stability results of BSDs, and then coupling it with the new approximation error that comes from the approximation of the second BSD. So by a careful accounting for the error propagation through the different stages, we can find the error in our XVA simulation, again, as a time-stepping error, as here in the last line of my slide, plus an error of basically the hedging error of our derivative portfolio, plus the XVA error at the terminal time. So this would be a posteriori way of quantifying the error in our simulations. Now we've cooked up a simple example here where we again know the exact answer. So switching off now the CVA and DVA terms by basically setting the hazard rate to 0. So there's no default of the counterparties, but still allowing for different funding streams. So we have different rates for the collateral in this case, and the borrowing and lending rates for the counterparty. So by having this differential in the interest rates, by basically mapping the multi-curve phenomenon, as it's also called, we are able to create a non-trivial funding valuation adjustment, but we're still able, by sort of tweaking the interest rates in the bond pricing formulas, we're able to compute this adjustment analytically. And in this case, this is 0.0092. But of course, we're interested in using this only to test the accuracy of our Deep XVA Solver. So if we run this heavy machinery that I've developed in this talk, by first simulating the value of a forward in this case, using the first BSD, and then writing down the BSD for the FVA, and sort of bringing this all together, using a similar architecture to the one that I showed you before, we get a FVA value of 0.0395. So there's an error which is about a fraction of a percent of the FVA, or quite small compared to the strike price of this forward. So this is just a proof of concept that we can indeed use this nested deep BSD solver to compute these higher level valuation adjustments. But we haven't explored further how much we can push the accuracy, the contracts, etc. So this is very much work in progress. And this brings me to sort of the conclusions and outline and future extensions of this work. So we have, by a sort of proof of concept study, tried to use deep solutions of BSDs to apply them to models of counterparty credit risk. And we've seen that the results are encouraging in the sense that we can both approximate high dimensional problems well. In this case, I showed you a 100-dimensional example. But also we can deal with the recursivity of the structure of these valuation adjustments in a natural way, compute hedge ratios, etc., etc. So a lot of the quantities that are of interest to practitioners come out naturally out of our framework here. I've also shown you that the collateral is also a natural byproduct of what we are doing. Now, one can, by further nested simulations, push this further to other adjustments that are being computed partially in the literature and in the industry. So I'll refer you to some of these plots that, these nice plots that Stefan Crepé always has about the CVA tree, where you have these multiple stages of valuation adjustments, starting from the CVA up to the funding valuation adjustments, and then further going on to capital adjustments, and further on. So this can be mapped into our framework by further recursive applications of our solver in principle. What's also interesting is, so I've, for simplicity, restricted myself here to what is called a single netting set, so a simple single counterparty, but of course in practice banks are exposed to trades with many counterparties, so it will be interesting to formulate this sort of as coupled systems of BSDs, where you then would also benefit from risk mitigation across different netting sets. And you could also think about modeling default contagions across counterparties. So there's interesting further feedback effects that can be captured in such models. And finally, to make this actually applicable in practice, we would either, on the one hand, want to push the accuracy to a practically acceptable level, consistently across different contracts, and also run this on more complicated models, contracts, etc., which in principle is again something that is encompassed in this model quite naturally. So finally, let me point you to a preprint, which is still slightly work in progress on the archive. And if you either want to verify my numbers or are interested in extending this further, there's also the code used to generate all these results is in Alessandro's GitHub directory, where you can use it and extend it. So I'd like to end here and look forward to any comments and questions.
So thank you very much, Christopher, for a very nice presentation with overview parts and details with the BSDE solver. And there are some questions on the chat. So for example, let's first take Shashi's question. Was there a particular reason to use two hidden layers in most of the examples used?
No, not at all. This was just a starting point, and we saw that already with two hidden layers, we got very good accuracy. In fact, we often saw that increasing the number of hyperparameters led to more overfitting or more sensitivity, in a sense, to the learning rate schedule. So it was more that this was already a parsimonious and sufficient for the examples that we looked at.
All right. Chris asked on slide 19, you have played with the effect of any other, have you played with any effect of activation functions other than ReLU for the accuracy?
I believe we have tried things like arc10 type functions, but the accuracy was quite similar. So there could be a potential benefit for computing higher order sensitivities because of the nature of ReLU of just being piecewise linear. But I think the accuracy would be quite similar. I think it's sort of the convenience of differentiation, if that was of interest, well, both for the fitting, but then also for potentially higher order sensitivities. I mean, ReLU functions are in a sense natural for standard derivative contracts because you can approximate or you can map the payoff exactly. We haven't played around a lot, but the preliminary observation was that using some smoothed out ReLU functions, something like arc10s or so, didn't have a material effect on the accuracy.
All right, thank you. Edouard asks, you reproduced the Black-Scholes value of at-the-money options. Did you try with the fixed neural network without any changing or recalibrating to reproduce also out-of-the-money option values?
No. So the simple answer is no, we haven't, and that would be a good thing to look at. So yeah, plot, investigate the accuracy as it changes. I mean, it could well be that. Yeah, so what I would say is it's very speculative. So no, the short answer is that no, we haven't investigated.
Okay. Al-Hachi Ali, how do you estimate the neural network error a posteriori? So
in this example, for instance, we looked at cases where we have an analytic solution, or we can benchmark it against a simple, straightforward Monte Carlo simulation with a lot of scenarios. But what we would like to push this to is exactly this a posteriori errors here. Where there's this theoretical result that allows us to compute or express an upper bound, which depends on some expected loss function of the final state. So in this case, we'd be looking at, for instance, the middle term here, the VT minus VT, so rho theta psi. So rho here are the neural network parameters. So this second term is something that it is something that comes out of the computation. So we can, whereas the first term is exactly the payoff of the option. So these are computable quantities that come out of our simulation, and by just sampling a reasonable number of paths, we can estimate these terms on the right-hand side. So that would be the strength of these formulas, that we can indeed compute these a posteriori bounds. So then if you find that they're insufficient, then we can think about well, increasing the complexity of the neural network by adding more layers, more nodes, etc. But that doesn't give us a structured way of thinking about this. But there's sort of a parallel line of research that I looked at recently, which is using recent results by Kai Gisek. So they look at explainability of neural networks and have a way of conducting significance tests on neural network parameters. So I felt that would also be an interesting thing to bring in here, to not just use your neural network as a black box, but actually test the significance of different feature variables and different even hidden layers to then come up with the significance, and that would give you a more clear recipe about how you would adapt your neural network to improve the feature. Whereas at the moment, this is all very experimental. And it's not always guaranteed that you do get any reduction in the a posteriori, or indeed the a priori error by increasing the network architecture. And my feeling is that often this is not so much an effect of the architecture as such, because we know from recent theoretical results by well, Arnold Jensen, Martin Hutzenthaler, and others, that for this type of pricing problems, simple control problems, the neural networks, they have very high expression power such that they can approximate derivative prices or valuation adjustments possibly in polynomial complexity in the dimension and in the inverse of the accuracy. So we know that by investing more layers, etc., we should be able to bring the error down as much as we like. But I think there's usually, we found a barrier in the accuracy of maybe a fraction of a % or so, but that is therefore due most likely to the inability that we find the optimal network. At the moment, it seems that the optimization methods are just not good enough to find the global optimizer in these problems.
All right, maybe two more questions that are on the chat, and in order to stay a little bit within the time, I see Carlos' question can lead to a short answer, I guess, Christoph, because the optimizer fitting the weights, is it stochastic gradients?
That's correct, yeah. Stochastic gradient, and we've played around a bit with learning rates, but it's fairly straightforward. Yeah, stochastic gradient.
All right, and as a final question from Nestor, how does your method compare to the others shown on slide 12? So.
So we haven't done any benchmarking to compare it directly. So it's just, yeah, it's a completely different beast with the complexity coming through to the fitting of the network. So I think it's certainly the most similar to the last bullet point here of Stefan Cabez and co-authors who also use BSDs, although they use a very different solver. It's certainly for whole books of derivatives and in high dimensions superior sort of to the middle block here that are partially based on PDs. And I would also think that because of their ability to look at these higher level valuation adjustments, it is also should also still beat sort of the traditional Longstaff-Schwartz type methods. But yeah, it would be interesting, for instance, to compare the performance to some optimized nested approach, which for some reason is something that doesn't seem to be very popular in banks, although that seems a very generic way of looking at it. So it would clearly be interesting to demonstrate the hopefully superiority of this approach compared to sort of a more naive nested approach.
All right, thank you. And I think you address at the same time Alexander's question, why using neural networks? I think it is the dimensionality, the BSDE to address the delta. So, and the whole book, I think it is the robustness and the generality, right? So thank you very much again, Christoph, for this talk. And